So we are about to prove the central limit theorems for the random walk in divergence-free drift field. So recall that the walk, okay, I don't write again everything on the blackboard because so this is a random walk on ZD such that at a random walk in random environment is stationary and ergodic, space-wise stationary and ergodic random environment. The inflowing flux and outflowing flux are the same at each single point. That makes it doubly stochastic. And I will and the statement was the following: take a random walk in random environment like this, make some assumptions, namely what I called ellipticity, which means that the symmetric part of the jump rates is bounded from below by a positive constant. And actually in my proof, I will take the symmetric part of the jump rate just constant to make things simpler. The theorem is more general, way more general than that, but we don't have time for all details. And the other constraint was what? The other constraint was that the drift is zero mean. You don't have an overall drifting, an average drift in one direction, so the random walk is diffusive. I mean, that's what I expect, it's diffusive. It's not drifting ballistically away. And the famous H-1 condition. That's the clue. Without the H-1 condition, the theorem probably is not, or the central limit theorem probably is not true. I have counterexamples. I don't have a proof of the contrary, that if and only if probably this is not the case. But for now, the H-1 condition. And recall what the H-1 condition had. I formulated in 4 different disguises. The first one was about a sort of infrared bound. By infrared bound, I mean some bound of the behavior of the Fourier transform at small values of P, of the Fourier variable, right? That means high frequencies. Anyway, which I don't repeat. That means essentially it means a sort of decay of correlation of the drift field, but it's a subtle thing. The second equivalent disguise was, I mean, what do I mean? That the drift field B has this property, right? The drift field is the drift field given by the anti-symmetric part of the jump rates. So the anti-symmetric part essentially is the same, that the anti-symmetric part of the jump rates have this property that their decay at far distances, their correlation at far distances have some decay property which ensure that this behavior of the Fourier transform. More equivalent to this one was a second one formulated in terms of random walk in random scenery. I'm not going to repeat it because technically we don't use it. But the ones which I will use technically, 2 more, is that the drift field or the anti-symmetric part of the jump rates be in the range of square root Laplacian, or which is the same in the domain of 1 over square root Laplacian to the minus 1/2. That's exactly the same thing technically. And yet another equivalent formulation, these 2 will be of importance, is that this sort of, which I call the stream tensor, that's a tensor field to which this vector field, which is the anti-symmetric part of the drift of the rates, so that tensor field be stationary and square integrable. In principle, it's only of stationary increments and square integrable. This is a special constraint that it be stationary, right? So this corresponds in 2 dimensions to a height function. In more than 2 dimensions, it's difficult to write it down. Now, okay, here we are, and now I want to prove, okay, we are in the Hilbert space. We are in the Hilbert space L2 of omega pi, and remember that I introduced a number of operators like like a gradient, a Laplace operator, the Riesz kernels, and some multiplication operators, right? And the infinitesimal generator looked like this. Now assume I made a special choice of the symmetric part being simple, being just constant, because that just complicates notation and adds some complication in the proof, but it's not essential from my point of view. Let me just repeat. The main message of all these lectures is that things can be done in the non-self-adjoint case. So I emphasize the non-self-adjointness. Therefore, I say that, okay, let's take the self-adjoint part as simple as it can. So this will look like Laplacian this field, in this space, plus sum over all possible neighbors. And remember, I had this m sub k gradient k. M sub k is multiplication with v sub k, the function v sub k, which is a bounded function, right? And this is the gradient in that field, right? And we also had, this is the same as Laplacian plus minus sum over k in E. Probably I will have to put Laplacian minus k mk. Due to the divergence-free character of the drift field is equivalent to this commutation relation. I showed it, right? Now, and my point is, remember this is the symmetric part, or minus one. So this is minus s plus a, the symmetric part and the anti-symmetric part. And recall that my main condition in this abstract sort of theorem, my main condition was that I can say something about the operator s to the minus 1/2 a s to the minus 1/2. I put it between quotes because though these operators are all bounded, this is unbounded, so you have to be very, very careful how to define it, what this object is, right? Now, before, I also said something, namely that many things were done much before, namely when the stream tensor is bounded, not square integrable, but bounded, that enters into this class of, okay, that has been done much earlier and many things have been done. And I said that in that particular case, the strong sector condition is applicable, and that's why people didn't prove it with that. There are many other proofs because other ways of proof there exist. But when the stream tensor is bounded, then mind m sub k f is multiplication of v sub k times f. It's a multiplication operator. Remember that. And I said when this arises, v sub k arises as a curl of h sub kl with the symmetries. This was the stream tensor. And I said that this be L2 for me. So this should be L2. In a later application, it should be L2. In a later, a bit stronger theorem, it should be L2 plus epsilon, right? But I also said that if it's L infinity, if it's bounded, then the strong sector condition applies. And I want to show you this thing first, right? If this is bounded, and due to this object, I tell you what happens, and I leave some elementary manipulative computations, not deep computations, just manipulation with translations, various elementary things. Then you can write this part. Then you can write this part. So in this case, introduce the multiplication operator n sub kl like this, n sub kl f be h sub kl times f. A multiplication operator. This is a bounded operator since now it's assumed that this is a bounded function. Right? And I leave it for you as an exercise, homework for you, easy homework, just elementary things, that in this case you can write L like Laplacian, and the second part can be written sum over k and L in E of, if I'm not mistaken, here I have a minus k and kl L. There is no surprise here. These are just discrete versions of the following, which you know well if you have done an elementary multivariate analysis. This corresponds to the following. Just to take off the mystery. So if in RD I have V is a divergence V is a vector field, and it's divergence free, right? And if you write V as curl of H, okay, now, yes, then you can write V times gradient like curl of H times gradient. This is in continuum. And this corresponds to that type of thing. Just that there is no mystery here. This is just elementary multivariate analysis that say on the lattice. But what matters is that this is a bounded operator, a bounded multiplication operator. Now if I write this in this particular case, I have, so for, let me call this B, in this particular case I will have B equal to Laplacian, okay, sum over KL in E, Laplacian minus 1/2 gradient minus K n KL, and again right, but these are the Riesz kernels minus K, and in between them there is the n sub K and L, and these are all bounded operators. So in this particular case, this operator of mine is a bounded operator. I have two Riesz operators which are bounded, and in between them a multiplication operator which is bounded. So a priori it is only densely defined and you have to be careful, but there is a uniform bound on its norm, so it's extended as a bounded operator. So I can write B, so in this particular case B will be a bounded operator. And from start it's skew symmetric. It's skew symmetric. Now if it's skew symmetric and bounded, then it's skew self-adjoint. That's just elementary, if you want, okay, it's not linear algebra, but it's elementary functional analysis. A symmetric and a bounded, everywhere defined bounded operator which is symmetric is by force self-adjoints. And a skew symmetric which is bounded is by force skew self-adjoint. Nothing to prove. Right? So in the particular case when H is bounded, and these are the cases when, for those who know something of this, the finite cycle decomposition of, well, the walk has finite cycle decomposition, that's some catchword for those who know, then the strong sector condition immediately applies and we are done. So I have to struggle now for the case when this is not, when I can't do this. When H is genuinely unbounded. H is just an L2, a square integrable function. Then I do two different things. I have these two forms of B. These are, as long as you only see bounded operators on your blackboards, these are just equalities, no problem. Now I try to define the B. I define the B given these two forms. Let me start with this one, and let me make an attempt. I call B, I define B as this one sandwiched between 1 over square root of this. So that will be sum over k, gamma k, mk, gamma minus k, mk, probably a minus sign is here, mk Laplacian to the minus 1/2. This is one of my forms, and I have to be careful how to define it. And the second one, and let me call it B star because I know what it will be. But I left room here to say where is it defined, because in a case of unbounded operators, I have to be very, very careful where I define it. And B star is, take the other one. Take the other one. I have Laplacian minus 1/2. I have sum over k, mk, Rees kernels. Is it right what I'm doing? Yes. Yes. Okay? I know where to define this one, because if I understand well, this is a well understood operator. This is just like square root of Laplacian. It's something given in terms of translations. It's well understood. I take a function from the domain of this operator, that is the range of Laplacian to the minus 1, to the Laplacian to the 1/2. I land here, but the rest are bounded operators. I don't have any problem. So I defined this on the subspace, where the subspace is H minus 1. Remember, H minus 1 was exactly the space, the domain of this operator. It's dense in the Hilbert space. It's not the whole Hilbert space. Dense in the Hilbert space. If I take a vector from this subspace, this funny object is well defined. Now I have to be careful about this, because it makes sense for functions which by this bounded operator are pushed into H minus 1. Right? It's an abstract thing. It may be empty. It may be empty. This is an operator which is a bit hidden. It's not at all the case that its range is the whole Hilbert space. It may be the case that it simply doesn't put any function, any vector there where it should. Let me define, anyway, it makes sense to define B star is defined on something I call B star, where B star is the space of those elements of my Hilbert space, such that, say, let me call this is, okay, such that A, this is minus A, doesn't matter. This is A. Such that A, because I put it better. Such that sum over K, mk, gamma K of phi is in H minus 1. It's an abstract definition. It might be none like that. I didn't say that it's not an empty set. I just said that this makes sense as a definition. Right? Now here are some elementary, okay, again, elementary in the sense I don't have, these are long story, as you see. So I don't have time to spell out all details, but you find all details in the paper which is attached into there. So here are some elementary facts. Okay, facts, which are easy to check, and I leave it for you as a homework or to check from there. These are few lines. So when I say facts and easy to check, I mean that by standard calculations and manipulations with symbols, pushing here and there, adjoining, and so on, you can check it. It doesn't. You don't do it in 5 minutes. You do it in 2 hours, say, if you are not experienced. Is the following. First of all, this is not empty. So much not empty that B is subset of B star. So if I take an element from H minus 1, which I know is dense, then certainly this makes sense. I can easily convince you on the blackboard, but I won't do that. If you want, I can take, okay, let's do it just fast. Let's do it just fast. So mind that the Riesz kernel is gradient times Laplacian to the minus 1/2, right? If it happens that my vector is in H minus 1, then I can just separate the Laplacian minus 1/2 and act with it. I get a vector here, gradient and m commute like that. I push the gradient back here with the commutation, and I get bounded. So actually, not only that B is like B starred, where B is included by D starred, but B starred restricted to B is equal to minus B. Due to these, anyway, my intention was that this be the adjoint. I might make mistakes with signs. I might make mistakes that this minus is not needed there or something. But my intention is that in the end, to arrive there. So B star, okay, this is abuse of notation for the moment. It looks like an adjoint. But so far it's just a symbol, right? So from just looking at it, from elementary considerations, I see that this operator is an extension of that operator. A second fact, okay, maybe it's not the most logical order, facts, first fact. The second fact is the following. If phi and psi are in B, I show that this B is skew symmetric. Then phi B psi, then phi B psi equals minus B phi psi. That's elementary computation again. Mind, I assume that both these guys are in B. Right? Now, if B was a bounded operator, then this would be true for any phi and psi, and that would prove that B is a skew self-adjoint operator. But that's exactly what I'm struggling for. You know? This is again an elementary computation. A third fact is that actually, and here comes slightly something which is a subtle thing from unboundedness, that B starred as defined is a closed operator. It's closed. Now I have to recall what the main, for those, anybody familiar with unbounded operator, or hands highly up, who bravely can say that they know what the importance of closeness of an unbounded operator is. Come on. So the problem with unbounded operators is the following. Now, I'm sorry, I have to go to the deep. This is partial differential equations. You have taken courses in partial differential equations. You must know. The problem with unbounded operators is that with concrete unbounded operator is that you don't have, that you define them only on a convenient subspace originally. Take the Laplacian, the normal Laplacian on R2, second, or derivative maybe. Take L2 of the interval 0, 1 and take the first derivative as an operator. You define it for what? For functions which are in L2 but are C1 and their derivative is also in L2. This is a dense subspace in L2. You define the operator in a dense subspace of L2. You draw the graph of the function in L2 cross L2. Here is the value of the variable, here is the value of the function, of course infinite dimension. You get a graph which is a linear subspace of this product space, right? Now if you want to make things work, you must have this graph closed. If this graph is not closed as a subspace of the product space, then you are fully lost, you are not able to do anything. That's what von Neumann realized back in the 20s, that this is the most important thing. But the bad news is the following. You took an operator which you thought is a reasonable object, for example, the first derivative, but you didn't care about boundary conditions. Take the graph, close the graph in that infinite dimensional topology, and you get a set which is not the graph of a function. When you close, you get a set that above every point you have infinite linearity points, so it doesn't define anything. So this can go wrong. This is why you have to define boundary conditions for partial differential in problems of differential equations, right? Otherwise, the problem is not defined. And therefore, the only if you have unbounded operators, then you have to make sure that the graphs are closed or closable. That means that if you close, you don't get nonsense, as I said. Nonsense means more than 1 point above one. And I leave it for you to check that this guy, as defined here, we showed already that it's at least densely defined because this subspace is included there, and this is a dense subspace, so this is densely defined. And it's not difficult to check that it's actually closed. So its graph is closed as it is. You don't have to, I don't say closable, I say closed, right? And actually, what you can, these are still among the easy facts, that B star is indeed the adjoint of B. Okay, B star, let me say it. B star between quotes is indeed B star. And you understand what I mean. So far, the star was just a misuse of notation, but I used that notation because I knew what I'm going to tell you. So if I define B like this and B star like that, then this will be indeed the adjoint, the closed adjoint operator of that operator. Now what can go wrong? What can go wrong is the following. When I close the graph of this guy, I get something less than that guy, not the full thing. When I close the graph of this guy, this is the adjoint of that, I proved already this claim. But the closure of the graph of this guy could be not the whole thing. And that's bad news indeed, and that happens indeed. And these are pathologically looking cases, but it happens, and you have to struggle against them, that you have an operator which looks like very nicely self-adjoint, you formally integrate by parts, and you get self-adjointness and all that. But if you analyze, it's not self-adjoint actually, and what it manifests in is that its spectrum is not the real line, but it's the whole complex plane, for example. I speak about skew self-adjoint, so I struggle for the spectrum of this guy be on the imaginary line. So what I am struggling against is very clear now. I have very concrete objects. So far my theory was abstract, but this cannot be more concrete than that. Very concrete operators. I know that much thing, but it could happen that the closure of this operator is closable. It follows from elementary fact. It's closable, so its closure is a graph. It must be a graph because its closure is contained in the graph of that guy, and the graph of that guy is a graph. So the closure of this guy must be a graph. That problem doesn't arise is now that the closure of this graph, of the graph of this operator is not a graph. But it may happen that the closure is less than that, and then I'm lost. So that's what I'm struggling for. So what I know so far, is that B defined on that curly B is skew symmetric. I know that closable. I know, let me call by B bar its closure. That means the operator given by the closure of the graph. clearly this is extension, which is included in B starred, or say minus B starred. By inclusion, okay, extension of a linear operator or inclusion of the graph is the same, right? Which I know well, but I have to prove equality here rather than inclusion, right? And there is a famous, this is a classical problem, okay, classical in quantum physics. So classical in the 20th century mathematical physics, because when people realize that there are these operators which formally we handle and manipulate with, and it's not clear what they are, and there can be big troubles arising. And there is a famous theorem of von Neumann's criterion. Of self-adjointness, in my case of skew self-adjointness, it's the same, of course, it's just change some i's to -1s or something like that. Is the following, here, this is a deep theory actually, that the range of B, okay, in my case, I have skew, not self-adjoint, it has skew, B plus identity and minus identity could be dense. Which is equivalent to saying that the kernel of B starred plus minus identity be 0. So what I have to check, this is deep. This is, so for those of you who know semi-group theory and theory of unitary groups and of operators and semi-groups, you recall Hille-Yosida theorem, and those Hille-Yosida, hands up who have heard about Hille-Yosida? So this is a counterpart of the Hille-Yosida, of part of the Hille-Yosida theory. Okay, the other way around, this was older than Hille-Yosida. So this was the inspiration for the Hille-Yosida theorem. So what I have to check von Neumann. Okay, I just erased the operator, but I will come back to it. I have to check von Neumann. This is an operator given, and I have to check that for any phi in B starred, B star plus B star phi plus phi equals 0 implies phi equals 0. This is what I have to check. Let me make a very, very elementary remark which will enlighten, I think. It is trivial for phi in B. It is trivial. Take a phi in B and use skew symmetry of the operator. Use the fact that B star confined to B is equal to B, and use anti-symmetry of B, and you get it. Is it clear what I'm saying? Is it clear what I'm saying? So for phi in B, this is trivial, so that's why it's a bit misleading. You say that I'm trying to prove trivialities. But the point is that the domain of B star is bigger. It's implicitly given. You don't have a very explicit form of the domain. It's not the case that you can explicitly identify. You can identify explicitly those in H-1 because those are easy to identify, but the rest, so you have to struggle for it, and you will see a proof of this now. You will see a proof of this. And it's surprisingly geometric and probabilistic. It looks like absolutely abstract function analysis, what I was speaking about so far, but it's down-to-earth probability and geometry, if you wish. Good. So I write down the equation as I should. So mind, B starred was Laplacian minus 1/2 sum over m, sum over k, mk, gamma k. That was B starred. This was my B starred, right? Phi plus phi equals 0. This is the equation I'm writing on. Mind that phi is in the domain of this operator, so I know it's in that crazy dense subset which, taking it, acting with this operator, will land in H minus 1, right? So it makes sense. Good. I apply, this is an equation in my Hilbert space. I'm allowed, so these are vectors. This is supposed to be a vector in my Hilbert space. This is supposed to be a vector in my Hilbert space. I'm allowed to apply a bounded operator to that. Let's apply the bounded operator Laplacian to the 1/2. Apply the bounded operator Laplacian to the minus 1, to the 1/2. I get the equation sum over k of m k gamma, probably some minus is somewhere which was minus. No, this doesn't have a minus. Mk gamma k is good, okay? Of phi equal plus Laplacian to the 1/2 phi equals 0. This is my equation. I have to show that this eigenvalue equation doesn't have solution, doesn't non-trivial solution. And note that you don't see any unbounded operator here. These are all decent bounded operators. So I reduce the problem. You don't see any unbounded operator. It's a very down-to-earth problem. I have some bounded operators given in my Hilbert space, and I have to show that this combination doesn't have 0 eigenvalue. Right? Now, what do I do? Give me a second to recall what I do. Let me denote gamma k phi. So this is a tentative solution. I don't know whether it's an assumed solution. I know phi is from that space. Right? Denote this guy u sub k. Yeah. Now give me a second. Yeah. Give me a second. Let me have a look. Give me a second. Yeah. And note, recall that gamma k was Laplacian to the minus 1/2 gradient k. And recall also that sum over k, gradient k, was equal to Laplacian. Mind, sum over k gradient k takes differences. If you sum over those differences, you just get Laplacian. Is it clear? Is it clear? Right. So from here it follows that I can write Laplacian to the 1/2. Give me a second. Laplacian to the 1/2 to the 1/2 phi. Okay, let me see what is sum over uk gradient k. Well, sum over k uk. From here it follows that sum over k uk is what? Sum over k uk is Laplacian divided by Laplacian to the minus 1/2. Okay, it's Laplacian times Laplacian to the minus 1/2 of phi. Which makes sense. It does make sense because this is like Laplacian to the 1/2 with a sign. Right? So this operator, plug it in here. So what we get from this, we get that sum over mk uk sum over k mk uk plus sum over k plus Laplacian. Give me a second. Don't I do something? So this added, so this is Laplacian. No, it's nonsense what I'm saying. Sum over UK is, let's see, let's make it. Sum over UK is sum over k Laplacian to the minus 1/2 Laplacian phi, gradient phi. I'm lost a bit. Give me a second, please. Yes, what I want to say that this is sum over UK. Just I lost the sign somewhere. I'm sorry, Laplacian is minus. No, I didn't lose anything. Laplacian is simply minus absolute value of Laplacian. Yeah, I'm right. So this is Laplacian to the 1/2, or maybe minus Laplacian to the 1/2. Yes, this is the case. I fooled myself. This is simply true. So let me do the other equation. In Neumann's case, you had two things to check, with the plus, with the minus. And I will check it with the minus, not with the plus. The two go exactly the same way, right? So I check the one with the minus sign here, not with the plus sign, because that will give me the direct things, and I will tell you what to do with the other one. Good? This is the equation I check. This is the equation for which I prove that only phi equals 0 is a solution, right? But that equation is now, okay, sum over k mk uk plus sum over uk equals 0. Which is the same as, okay, let me mind that mk is a multiplication operator. So this is a v sub k, and let me write it omega almost surely 0. This is the equation I have to show has no solution except u identically 0, right? And here comes a very important, maybe the most important thing. This u sub k is a gradient. U sub k is a gradient in the sense that u sub k omega plus u sub l tau k omega equals u sub l omega plus u sub l u sub k tau l omega. It's a gradient. Why? Because it arises, if you look from there, it has. But the point is that it is not necessarily a gradient of an L2 translation invariant object. So it has the symmetries of a gradient, but it may be the case that there is no translation invariant field, no stationary field to which it is a gradient. And that's the main point. That's the difference of the domains here I defined. So it may be the case that this guy is the gradient of a field of stationary increments. And that's the point. So it follows that I can lift this equation I have to go out from my context of the Hilbert space because I have to lift it to, I will have a function which is of stationary increments, not stationary. So it's not translate of an element, the values are not translates of an element of the Hilbert space. Is it clear? So I lift this equation, so that means that, it means the following, that there exists U, capital U, x omega, which is a co-cycle, which is a field of stationary increments, such that u x plus k omega minus u x omega is u k tau x omega. So that the translates of this guy form the gradient of a field which is itself of stationary increment, not stationary. Right? So this equation, if I lift it to ZD, now I lift it to ZD, this lifted to ZD will give me sum over k v sub k, I write now x omega times, yes, plus 1. This is plus 1 comes from here, of u x plus k omega minus u x omega equals 0. Sorry, like that. So what is this equation? This equation, it looks like a harmonic. If let's say, let's look for a moment. Let's take this v0 for the moment, and it's a homework. I give you a homework. If the v is not there, this tells you that the function u is harmonic. The function u is harmonic. That means that at each single x, sum of over the neighbors minus 2d times sum at x, minus 2d times the value at x gives 0. This is harmonic. So if this guy is not there, this shows that u is harmonic, right? And here is a homework for you, in particular for those who like harmonic analysis and things like that. Show that there exists no harmonic function which is of stationary increments, random harmonic function which is of stationary increments and 0 mean. It's not trivial. So I am looking for a field on ZD which is of stationary increment, random field which is of stationary increment with ergodic and stationary increments, 0 mean and harmonic. Show that there is none like that except the constant. Except the 0, because I assumed 0 mean. Is it clear what the question is? Right? Now this is, and okay, how do you prove it? It's not a simple, okay, it's a homework. Indeed, this what I gave you is a homework. It's not totally trivial, but the idea between quotes is the following. A field with stationary increment has sublinear increase. With 0 mean, I always speak about 0 mean fields. 0 mean field with stationary increment increases sublinearly towards any direction towards infinity. On the other hand, we know from classical analysis that harmonic functions either are constant or increase at least linearly somewhere in some direction, right? But this doesn't work, this proof. Doesn't work because what it means that a field of stationary increment be sublinear is a very subtle thing. The ergodic theorems work in one dimension, and you have to be very, very careful with ergodic theorems in more than one dimension, what is true and what is not true. Right? So this is a subtle thing, but nevertheless, without the v is a good exercise for someone who is knowledgeable with harmonic functions and Brownian motion. But what you notice, so my goal is to prove that this equation you see here doesn't have non-zero solution. U equals identically 0 is a solution, of course. I assume U is 0 mean because it's gradient. If you have, okay, 0 mean, except for you always can take a linear function which will solve it, but that's no good. That's not what I want. So take it 0 mean, and I want to show that it doesn't have non-zero solution. Now notice, from now on I will go, unfortunately I will have to use the same symbols because there are not so many more symbols, but Laplacian from now on will mean Laplacian on the lattice. So this means the following, that this means what? This means what? Assume you have a solution. Assume U is a solution, right? This is, at X, this is exactly the Laplacian of the random walk in random environment, fixed environment, omega is fixed. So this is the infinitesimal generator of my random walk in this random environment applied to U. So this is exactly the harmonic equation. This equation tells me that U is harmonic for my random walk in random environment with fixed environment. So it is the same as saying that no non-zero harmonic functions for my xt which are of stationary increment and zero mean. This is the meaning of the equation. Stationary increment with respect to the same randomness as the random walk in random environment over the same space. Is it clear what I'm saying? Is it clear? Hands highly up who understand what I'm speaking about. Highly. Okay. Good. So this is what I'm going to show. This is what I'm going to show, and I'm going to show it in 2 steps. I'm going to show it in 2 steps. Let xt be my random walk in random environment. Omega, I put quenched, fixed omega, right? And let me define something which I call, say, R of t, which is this presumed solution, U of xt. I presume I have a solution U for this problem, and I define a process, so this is a solution U, I define a process which follows my random walk in random environment and records the value at the actual position. Since this is a harmonic equation for my random walk, this will be a martingale. This will be for fixed, a quenched martingale. By quenched martingale, I mean that with fixed omega, this is a martingale, right? On the other hand, in the annealed setup, so if I take randomness over walk end, it's still a martingale. Of course, if it's a quenched martingale for almost all omegas, then you easily check that it's still a martingale in the annealed setup, and you will see that in the annealed setup, it's a martingale with stationary and ergodic increment. So it's in the annealed setup, it's a martingale. So by the martingale central limit theorem, I can conclude that the quenched martingale in the quenched setup, so that RT by square root of t converges in distribution to a normal with zero mean and some variance, let me call the variance rho squared because sigma is used already, where rho squared is computable. Rho squared is computable, and you will see that rho squared, this is again homework for you because it's an elementary computation for martingales. For stationary martingales, you can compute the variance easily, and by the ergodic theorem, the martingale central limit theorem, which is based on an ergodic theorem, the variance of this guy will be almost surely what I tell you is a constant, which is 2 or 1/2 or 4 or something like that, times the norm of that u, which I assume, okay, probably sum over k's. UK norm squared. Remember what the UK was. Because at each single step, your martingale, you compute how the martingale, how the square of the increment, what the conditional expectation. It's an elementary computation. Good. Now, if I'm able to prove, on the other hand, if I'm able to prove that RT by square root of t converges in probability to 0, it's a convolved proof, convoluted somehow, then it follows that this is 0. Implies 1 second, u is 0, and I am done. I should put this smiley, but I don't know how to draw it. Yes, question?
Sure, the French martingale property is exactly because of that equation of the right answer.
Yeah, this is the equation lifted to the lattice. This is the harmonic equation for my random walk, right? So the solution, what I have to prove, it turns out that the eigenvalue, if I do these manipulations and lift it and so on, the eigenvalue equation reduces, is equivalent to saying that this harmonic problem doesn't have non-trivial solution. And how do I prove that it doesn't have non-trivial solution? First I define a martingale, first I take this most natural, if I see that, if you see a harmonic equation, then you think about a martingale first of all, don't you? Do this martingale, compute its variance, which is this guy. On the other hand, prove that actually this martingale converges to 0, scaled with the square root of t. And this is coming. And this is coming. How do we prove this? Give me a second. And actually, I will prove that this converges in the quenched probability to 0. Quenched is sufficient. Not quenched, sorry, annealed. That's sufficient because the annealed, this will be the variance of the annealed martingale. So it's sufficient to prove it for the annealed. Okay, now let's prove this. Probability that RT is larger than delta times square root of t. Delta is a small number. I will prove that this goes to 0 as t goes to infinity, no matter how small delta is. Right? Is equal to or less than or equal to the probability that RT is larger than delta square root of t and xt less than k times square root of t. K will be a big number, plus probability that xt is greater than k times square root of t. Clear? And probability is annealed probability. These are annealed. I don't put the omega here, integrated. So either the random walker is further out than k times square root of t, or it's closer and this guy is big. We know from the h minus 1 only, the h minus 1 gives a diffusive upper bound. From h minus 1 it follows, from my abstract, one of my first abstract things, it follows that expected value of xt squared is less than some constant times t, some upper bound, whatever constant. So the h minus 1 gave me an upper bound on the variance. And I have the h minus 1. From here it follows that the second part, it follows that by Chebyshev or something like that, that xt larger than k times square root of t is less than or equal to, help me, c over k squared. Keep in mind, k will go to infinity. Remains the other one with fixed k. Remains the other one with fixed k. Now, probability that RT, let me see, can I, larger than delta times square root of t and xt less than k times square root of t is what? Is, now this is what I'm going to control, and here comes one of the most, okay, a very, very classical thing which I wanted to give you as a take-home message. Okay, first of all, by Chebyshev, let's do a very simple Chebyshev. This is less than or equal to, let's see, 1 over delta squared t times expected value of RT squared with the indicator of xt less than k times square root of t. Right? This is just Chebyshev. Now, there is something I wanted to emphasize today, but time is quite running out, namely Nash's inequality. Hands highly up who know Nash inequality. Highly, 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 highly. One single hand is up. It's so okay. I gave these lectures when I was invited, and I was very happy to be invited. I thought, okay, there are 3 messages I want to send when I give these lectures. One is the Kipnis-Varadhan theory. The other one, the Nash inequality, I'm going to tell you now. The third one will be another Nash stuff, which is coming tomorrow. So classical things which I think you should know. The rest is interesting, nice mathematics, of course, but these are the take-home messages. Now, a consequence, so I call it, so consequence, so I put it as a theorem, and it's a consequence of Nash inequality, which I'm going to tell you. Given, forget about random walk in random environment, right? Let's have a doubly stochastic random walk in deterministic environment. So I have rate of from x to x plus k in ZD. The rate is, as I said, my notation will be the same. So the rate is s sub kx plus v sub kx. It's deterministic. S sub kx is equal to s sub minus kx plus k, and this is equal to minus v sub minus k x plus k. And the condition is a double stochasticity, namely, I write it again, k v sub kx equals 0. So I have this type of random walk. The environment is not randomly selected. It's just you gave me deterministically nasty environment, non-homogeneous nasty environment. And I give one single condition, the ellipticity. That S sub k of x be larger than or equal to some positive lower bound altogether. This is all I assume, nothing more. No randomness, no translation invariant. You can have it very inhomogeneous environment, changing on different scales in different ways. The only condition being this. Theorem. There exists a constant which depends only on the dimension and this as lower bar or lower star and nothing else, such that for any x and y on the lattice and any time the probability starting from x that xt is at y is bounded above by c divided by t to the dimension half. You have an absolute uniform upper bound of the good order. Mind that in ordinary simple symmetric random walk, this is the order of the diagonal element. So you have an absolute upper bound of the order of the symmetric simple random walk, no matter with very, very huge generality. Now, this theorem has many proofs. The first proof was given by Nash. So this is John Nash. Exactly 60 years ago. So I want to celebrate this paper of Nash today and tomorrow. This is one of the most brilliant papers in the history of mathematics, at least 20th century for sure. You know about John Nash. Everybody knows John Nash's name, right? So he's known for what? For game theory. Anything else? Sorry? Say it again? Yeah, that's right. And also for analysis. He has two papers in analysis altogether. I mean PDE, analysis and PDE. One is this one, absolutely most influential and brilliant. Okay, I will tell you more about this. Now, this was the first proof. Then there are geometric proofs which rely on isoperimetric inequalities and things like that. There are combinatorial proofs, more recent by Yuval Perez and co-authors. Perez and Morris, actually, one co-author. So there are many, many proofs in different contexts, but Nash was the person who realized the importance of this and proved it. And not for random walks, for diffusion. He was interested in parabolic partial differential equations. He didn't, of course, he knew in the back of his mind diffusions, but not the random walks. Okay, let's assume this, prove it later. Let's assume this and close the proof of this thing. Right? If this is the case, I assume the ellipticity of my walk, so this is certainly true. Then I do have what? This is less than. Okay, shall I leave the rest for you as homework? I have 1 over delta squared. Yeah, I have to be attentive because I didn't look this morning at the details of this, but I will see. Yes, I have this. Yeah, okay, I have this. Now let's compute this. Let's compute as upper bound on this using Nash. So the distribution, no matter what happens. So what is the difficulty, by the way? The difficulty is that the random walk is coupled with the field. It's not a field and an independent random walk. The random walk is defined exactly in terms of those variables which define my field. So that's why there is no direct way of putting your hand on it, right? So I have a random walk and I have a random field, but the two are coupled. So therefore it's difficult to. But I know this upper bound, no matter what happens deterministically, this upper bound. Then I can give an upper bound to this guy. This will be sum over, or upper bound, sum over x less than k times square root of t. right? I have the field, the value of the field at that point. I have u x squared, and I have, give me a second, I have the upper bound. I have the upper bound, c divided by t to the d half. Yeah, and I'm about, what is that? No, no, sorry, an expectation is still there. So this is, so what did I do now? I computed the expectation with respect to the walk, an upper bound to the, with the fields fixed. So I have to take the expectation of the field, expectation of ux squared, and c by t to the d half, right? Now this is I claim that the limit as x goes to infinity, expected value of ux squared divided by x squared is 0. Mind, I said that the problem is that if I have a field of, we have to understand these fields of stationary increments, stationary and ergodic increments. If you have in one dimension a field of stationary and ergodic increment, what does it mean? It's sum of stationary ergodic random variables by the ergodic theorem with probability 1 u of x divided by x goes to 0. That's the ergodic theorem, right? In 2 dimensions, and actually it also follows that the supremum, the maximum of the field in an interval of size n divided by n goes to 0 almost surely in 1D. Now if you go to 2D or higher D, take a field of stationary increment. It increases sublinearly in principle, but locally it can have huge peaks, and there are very funny counterexamples. So you don't have this type of thing that the maximum of the field in a box of size n is small order of n. It's not true in more than one dimension, right? But it is true for the average. So locally you can have huge peaks and you have a non-anomalous behavior, but not in the average. So this is just the same as the L2 ergodic theorem in one dimension. You prove it in the same way as the L2 ergodic theorem in one dimension, as long as you take expectation, right? Now let's do this thing. So from here you put together things and you get it. Okay, let me just not do the computations now. Using that and using this, you get the following, that this converges to 0 for all delta and all k. And once you have that, let k to infinity, go to infinity. Okay, I don't finish this now because probably I will make confusion. It's very simple. So you just take that thing, implement it there, and you have very explicit computation. You will see that this converges to 0 as t goes to infinity, converges to 0 no matter what k and delta were. Once you have that, let k go to 0 and we are done. Yeah? So the message is that you have to struggle with the fields of stationary increment, ergodic and stationary and ergodic increments in more than one dimension, and that's how you can come around. If there was something like a 2-dimensional or 3-dimensional theorem like in 1D, that the supremum in a box of a field of ergodic, zero mean field of ergodic increments, the supremum of that in a box of size n is smaller than n, this is not true. If this were true, then we were done much earlier. But this is the problem you struggle with. Let me come back to this. Let me come back to this, to Nash. This is a very beautiful thing. How Nash proved it I will give you the analytic proof. I will give you the analytic proof, if I have it somewhere. In our paper, the combinatorial proof is reproduced, but I like much better the analytic proof, I must say. Maybe the case that I didn't take, no, I didn't take my notes about Nash anyway, but I will be able to, I hope I will be able to, oh, that's bad. With the many notes, I didn't take the Nash note with me. But I have a booklet. In the booklet, you find these handwritten things towards the second half of the booklet. And on page 5 of the handwritten stuff towards the second half of the booklet, you will find the Nash stuff. Okay, the Nash inequality is the following. This comes from that paper, right? Is the following. Now I change notation. I am on ZD. I'm on ZD. My notation now is all on ZD. And Laplacian is Laplacian on ZD. Okay, let me, before I state the theorem, let me fix notation. So I'm in ZD. I'm in LP ZD. Actually, for P equals 0, 1, P equals 1, 2, and infinity will matter and nothing more. Right? Laplacian of f at x is sum over k fx plus k minus fx. So it's the lattice Laplacian. Right? Nash's inequality is the following, and scalar product, if you see a scalar product, is a scalar product in L2, in this L2. Right? Nash's inequality is the following. There exists a constant which depends only on the dimension. This is small. When I write small c means positive. When I write big C means finite. So it is a positive, of course finite, but positive. The point is that it's positive. Such that f times minus Laplacian f. Laplacian is a negative operator, so I take, this is what I called absolute value of Laplacian before, is greater than or equal to constant times norm of f2 squared in d plus 2 to the power d plus 2 half times norm of f1 squared to the power minus 2 over d. First of all, check that the equation is homogeneous. So if you take a, so it makes sense. It's homogeneous. If you take a multiple of f, you get the same. Right? So what matters is that the L2 lowercase, this L2 norm and L1 norm enter into the game, and you bound above, you bound below this value. Yeah, this is true for any function. Good? Let's use that. I'm not proving that now. Maybe tomorrow I'm proving that one. Using that one, I want to prove this. If I have time left. I still have about 10 minutes. Good. So this is what I call diagonal heat kernel upper bound. DH, this is what I called in my notes diagonal heat kernel upper bound. If you are in the heat kernel story, then you learn that you must give this type of complicated capital letter denoted names to various inequalities and things, because that's what these guys use. So this is diagonal heat kernel upper bound. Good. Okay, let me denote. I will prove the following. I will prove the following lemma. I will prove the following lemma that take the semigroup PT. Now PT is the semigroup of this random walk on LP. PT is the semigroup on LP. So let me write it here. PT F X is expectation that your walk starts from X, F of Xt, which is a bounded operator on all these LP spaces. Actually, it's a contraction on all these LP spaces. By the way, I should have made the remark, which I didn't do, but I did many, many times, that this double stochasticity is assumed. In this context, it means that the counting measure on ZD, is invariant measure for the random walk. Right? So these are LP spaces over the invariant measure of the Markov chain. That's very important. And PT, due to that, PT defined there will be a contraction semigroup in all LP spaces. So this is not part of the lemma. PT are contractions on all. So all P to P, this is not part of the lemma. Norm of this guy is less than or equal to 1. That's from start. And now the lemma says the following. PT 1 to 2 is bounded by a constant which only depends on the, by the way, which only depends, this constant depends also on S lower bar. Okay, we'll make a remark in a moment. C, which depends on dimension and this S lower bar, times time to the minus d quarter. And similarly, of course, PT start, this is the same statement, 1 to 2 is less than C d S start the d quarter. This is the same statements because the backward walk has the same lower bounds, so it's just not a separate statement. But this is equivalent, so this is in parentheses if you wish, because it's the same. But this is the same as saying that PT 2 to infinity, the adjoint of this, is bounded by C times T to the D quarter. This is what I'm going to prove in a moment. But once we have this, of course, we have the statement. Once we have this lemma, this is the lemma to be proved, but the theorem follows from this because putting together this and that, we get PT from 1 to infinity. From 1 to infinity is bounded above maybe by C squared. Another C. C squared times T to the D minus, T to the minus D half. And this gives you the result because it tells you start, for example, take as particular case the starting. So from here it follows that okay, this gives the result. It's clear, isn't it? So the supremum, come on. Okay, take delta at x, p, t. Okay, let me not do it because I'm confused now. But certainly this implies the result. This implies the result. So we are done. We have to prove this. We have to prove this. So let me take an f, fix an f. Let me take an f, right? And call ut be the L2 norm squared PTF2 squared. This is, I call it, f is fixed, f fixed. Right? Now, which is the same as PTF. Right? Let's compute its derivative. Let's compute its derivative. We differentiate here. We get this is equal to twice. Differentiate this, you get the infinitesimal generator, right? You differentiate here, you get the infinitesimal generator. So you get twice, or you get L PTF plus PTF L PTF. L is the infinitesimal generator, which consists of symmetric and anti-symmetric part. But since this is the same as that, and this is the same as that, only the symmetric part survives. So this is minus twice PTF. S is the symmetric part of the infinitesimal generator, PTF. But mind that my rates were bounded from below by S starred. And that's why I have now here, this is greater than or equal to, the same with the minus Laplacian. So altogether this is less than or equal to, I have something like I have twice PTF symmetric part, I have 2S starred, and I put here a minus Laplacian PTF. I just use the fact that this operator is bounded below but by that operator. Right? And now I use Nash's inequality. So by Nash, this is less than or equal to, let me copy from here without thinking much. Okay, I put S star is included now in my constant. A constant minus a constant times PTF 2 squared to the power d plus 2 over 2 times PTF 1 squared to the power minus 2 over d. Do I have time to finish? This proof? Good. Minus 2 over d. And mind that this is equal to, no, this is less than or equal to, give me a second. Yes, this is less than or equal to minus c, this was u. Ut to the d plus half over 2. Mind, this is less than f 1 squared, because PT is a contraction. PT is a contraction in L1, so this is less than f1 squared. It's in a negative power, and it's a minus sign here. So I can write here f1 squared to the 2 over d, to the minus 2 over d. Right? So altogether what I got was, let's see, what do I got? What do I get? Let me better copy then. So what I got was the following. U to the t, I just copied from my notes because I don't have time now to check all. U to the t, u is a positive thing. To the minus 2 over d minus 1, I just divided by this. What did I do? What did I do? This is d here. This is d here. This is d, not 2. Sorry. If you go to the Nash inequality, that's d, not 2. And then it's correct, yes. Minus 2 to the minus 1 times u to the ut dot is bounded above by minus c times f1 squared to the minus 2 over d. And now I integrate this guy. And I get by after integrating, I get, okay, integrate, let me skip something. This is just a differential. You know how to integrate it. Let me integrate it and arrive at the end of the computations. Arriving at the end of the computation, I get u to the t, ut to the minus 2 over d is greater than or equal. I change because you see this is less than or equal than minus, but when you integrate, you get ut down and not up and so on. So elementary manipulations, you get this less larger than u naught to the minus 2 over d plus constant times f1 squared to the minus 2 over d times t, because we integrate. And now do what you have to do, and in the end you get ut less than, if you remove, okay, this is positive, you can take it away, and if you take the proper power, you get ut less than f1 squared constant times f1 squared times t to the d half times what? Times t to the d half. T to the minus d half. Right? Which is exactly what we needed. Because if you take square root, you get PTF. The L2 norm of PTF is less than constant times, take square root, you have t to the minus d quarter L1 norm of f. And it's done. It's elementary computation, but of course in the background is this ingenious Nash inequality, which I will try to show you tomorrow, how the Nash inequality comes. Good? Because it's a very important thing. So that was it for today, and we continue tomorrow. Thanks.